In this video, we're going to take a quick look at problem 109. The catapult is used to launch a ball such that it strikes the wall of the building at the maximum height of its trajectory. Now, if the ball kept going and didn't hit the wall, point B would still be the maximum height. So this is as high as the ball is going to go, even if the wall wasn't there, which means when the ball hits the wall, the velocity is in the horizontal direction. This is true when the object is at the maximum height of its trajectory. If it takes 1.5 seconds to travel from A to B, determine the velocity at which it was launched, the angle of release theta, and the height h. It's very interesting to me that they ask you for the velocity, the initial velocity in this problem, when usually they ask you for the initial speed, because they're also asking you for theta. But if they asked you for the initial speed and theta, you could put those together and get the velocity because you have the magnitude and direction. So I'm really only going to be worried about finding the initial speed and theta, because if we have both of those, we know what the initial velocity is. Okay, and note that the ball is launched 3.5 feet above the ground, and when they ask you for h, that is being measured from the ground. So when we draw our vector diagram going from the height at which the ball was launched to point B, that's going to be h minus 3.5. Okay, so we have all the information here. And we're going to use the fact that the velocity is horizontal when the ball hits the wall, and this equation, which we don't use that much because ordinarily we only need it when we are looking for the final velocity. So that's similar to equation 12.4. In this problem, we're not looking for the final velocity, but we need to use the information they gave us about the ball hitting the wall when it's at the maximum height of its trajectory. And I said in a previous video, usually we're not given the final velocity, so the only time we would use this equation is when we're looking for the final velocity, but in this case actually we have to use this equation even though we don't know the final velocity, because we're given information about the direction of the final velocity. So we can draw this vector diagram for this equation, and when you do the hypotenuse times the cosine of the angle, you get this here, which actually we're not going to end up using because we're not looking for the final speed. But when you do the hypotenuse times the sine of the angle, this side is the acceleration times delta t. The acceleration is 32.2, delta t is 1.5, that's 48.3. That doesn't tell us what the initial speed is, but that is the initial speed times the sine of the angle, so we're going to use that later on. Now we can go to the equation that we usually use for projectile motion, draw our vector diagram. We have delta s going from A to B. I know that the ball is going 18 feet in the horizontal direction, and it's going up a distance of h minus 3.5 feet. And then I have my initial velocity times delta t going off at an angle of theta from the horizontal, and my acceleration times 1/2 times delta t squared going straight down. Okay, so I'm going to take the hypotenuse for this right triangle here and multiply it by cosine theta, and that would be equal to 18. And then the hypotenuse times sine of theta is equal to the entire distance from here to here, which is this piece here. Half of 32.2 is 16.1, so this piece here is 16.1 times delta t squared, and this piece here is h minus 3.5. Okay, and then we're going to have to think a little bit about how we're going to solve from this point on. You could start off looking at equation 4, and this has a VA and a sine theta in, and I know VA times sine theta is 48.3, so using equation 4 and taking what you have from equation 2 and putting it in for VA sine theta, and then putting the delta t in here, you can solve for h, and we have 39.7 feet for h. For equation 3, I think it's just a little trickier. Well, it's actually not that hard. Okay, so we haven't found VA yet, but I know what VA sine theta is, so you could actually just take equation 2, divide it by sine theta, and sub that in for VA, but instead what I did was multiply by sine theta divided by sine theta. So if we take this and we multiply it by sine theta divided by sine theta, one of those sine thetas is going to stay in the denominator here, the other one's going to be it's going to stay in the numerator here. The other one's going to be in the denominator. That's cosine divided by sine, which is 1 over tangent. And then from this point on, you should be able to solve for the angle on your own. So finally, we need to know, well, they asked us for the final velocity, but let's just be content with finding, the initial velocity. Let's be content with finding the initial speed. And now that we know the angle, we can go back to equation 2 and we can find the initial speed. You can do this on your own, and you should find that it's 49.77 or roughly 49.8.